This section in the book is called reciprocity, but a better way would be to refer to it as Newton's third law. And the reason it gets introduced here is that because with the gravitational equation, it's very easy to see why these forces end up having equal and opposite magnitude. So if I'm going to call this planet 1, this is planet 2, and I would like the gravitational force on 2 by 1, that's going to be negative g m1 m2 all over r2 minus r1 squared, and I'm going to call this vector r21 hat. All right, and that's referring to the vector pointing from 1 towards 2. So this would be r21 vector, and then the unit vector is just pointing in that direction. So if we ask the opposite question, what is gravitational force on 1 by 2? Well, switching the two masses doesn't matter. The order is no effect on multiplication. Switching these two will switch the sign, but since we're taking the magnitude and then again squaring it also, we are going to end up with a positive number no matter what. So the ordering doesn't matter there. The only thing that's going to change is the direction of the unit vector. All that does is introduce a minus sign. So in terms of the magnitude itself, there's actually no change. The magnitude is the same for both cases. The only difference is going to be in the direction, and the direction is just going to have a minus sign. So we can say that F grav on 2 by 1 is equal to negative F grav on 1 by 2. They are equal and opposite. So the reason that this some people have a difficulty with this is, well, they're looking at these planets saying, well, they're two different sizes. How can this little guy be exerting the same force on this big guy as the big guy exerts back on the little guy? They have different masses. But the key is it's an interaction between the two masses. It's not that this guy acts by itself on the big planet and this guy acts by itself on the little planet. It's that these two things are causing an interaction, and so the two masses come into play. So we would refer to this set right here of forces, this set right here of these two forces as forming a single interaction. And we would refer to this force and this force as third law pairs. In other words, they form part of a single interaction. Now let's take a look at an example a little closer to home, and we have a coffee mug sitting on a table. And let's draw a few free body diagrams just to kind of help us get our heads around this idea of third law pairs. So my free body diagram for the mug is going to have F grav on mug by Earth. And if this mug is not accelerating, if its momentum is constant, the net force has to be 0. So there's got to be a second force on here, and that's going to be F, and it's called normal, on mug by table. So that's a free body diagram for the mug. Let's look at a free body diagram for the table. And imagine that this table has some legs, and it's resting on the floor, and we'll consider the legs to be part of our table. So the free body diagram for the table, we have F grav on table by Earth. Now the mug is sitting on the table and the mug is pushing down. So I'm going to run out of room here, but that's supposed to be an arrow. And this is going to be F normal on table by mug. Now, we got these two downward pointing arrows. The table's not changing its momentum at all, so the net force has to be 0, so I need an upward force, and that's going to be an F normal on table by floor. All right, so take a look at this force and this force. And you'll notice not only are they the same type of force, but they have the same two terms. They're just switched. So the mug is the target for this force. The table is the actor or the cause of this force. We have the reverse case here. The table is the target. The mug is the actor or cause of that force. So these two forces just have the actor and target switched. The reason is that these two forces are part of a single interaction. These two guys are not separate. This is a single interaction. And so these two forces can't be different. They have to have the same magnitude, and the directions are always going to be exactly opposite from one another. Now, looking at these other forces, let's take a look at this one here. F-grav on mug by Earth. So where would the third law pair for this force appear? Well, the third law pair, in other words, the other half of the interaction, comes from just switching the target and the actor. So the third law pair for this one would appear on the free body diagram for the Earth, and it would be called F-grav on Earth by mug. It would have the same magnitude as this force, and its direction would be opposite. So in other words, the mug is pulling up on the Earth with a force equivalent to the weight. Going over here and looking at some of these, we can see, well, the third law pair to this force is going to appear on a free body diagram for the floor and comes from just switching the target and actor. Again, looking here, the third law pair to this force is going to appear on the free body diagram for the Earth and come from switching these two as well. So really the key idea here is that third law pairs are part of a single interaction. They're always going to have the same magnitude because they are a single entity, and the directions are going to always be opposite.